A Maxwell-Boltzmann distribution is a graph that will show us the number of molecules moving at any particular speed. And this is a histogram of types. So it'll show you if I have a few molecules moving slow, a, more molecules moving at a higher speed, a greater number of molecules at that speed, etc. Eventually, it approximates a curve. I'm going to show you via a simulation what a change in temperature will do, and we're also going to look at what a change in molecular mass will do. This is a simulator that shows me molecules moving around, some of which are moving slow, some of which are moving fast. And over here, we have a distribution of the number of particles moving at a particular speed. Now, I'm going to take a screenshot of what we have here so that I can compare it in a couple minutes. Now, when I heat up the gas, watch what happens to this distribution over there. So it was at 450 meters per second. And now that I've heated it up so that the average speed is 740 meters per second, my peak isn't as high, but I have more molecules moving at a higher speed than I did before. The reason the peak isn't as high is the number of particles stayed the same, but they're distributed over a wider range. In other words, the area under the curve has to stay the same, even if my peak changes. I still have some molecules moving very slow. This does not end up being a normal distribution. And the reason why is the lower limit is capped at 0, but the upper limit is theoretically infinite. Based on chance, I can have some molecules moving very fast, but the slowest a molecule can move is 0. When we have more molecules in here, rather than this being a choppy bar chart, it starts approaching a more smooth curve. I'm going to take another screenshot so that I can compare this one later. Okay, now what I'm going to do is I'm going to add different particles. I'm going to add the red ones, which are smaller. And since they have a lower molecular weight, they're going to be moving at a higher speed. If I graph them separately, you'll see that their shape of the curve is a bit different. I don't know that I have the same number of particles of each. I'm going to check that. Of the light ones, I have 80. I'm going to increase that to 92. So just so that it's the same. Now you can see with the lighter particle, they have a higher average speed because of the fact that they're lighter. But if I look at the kinetic energy of each one, the kinetic energy of the two isn't very different. And in fact, all gases at the same temperature should have the same kinetic energy, or the same average kinetic energy, since temperature is a measure of average kinetic energy. What I want to do now is I want to connect the Maxwell-Boltzmann distribution to the probability of collision, or sorry, to the probability of a reaction happening. We said before that we need the kinetic energy of the molecules colliding to be greater than the activation energy. So suppose the activation energy requires the molecules to have a speed here. I would call that the threshold speed. If they're moving faster than that, they can collide. I'm sorry, they can react. So for my cold gas, we'd find that only these molecules had sufficient energy to react. So those molecules would react. The curve would redistribute. Some molecules would end up going faster than that threshold speed, and then they would react, et cetera. But if we were to compare it to the room temperature gas, for the room temperature gas, all of these molecules have sufficient kinetic energy to react. So since more of them are moving at the threshold speed, the probability of reaction increases as we increase the temperature. With the even hotter gas, all of these particles, a greater percentage of particles, have the energy needed to react. So we can sum this up by saying, as we increase the temperature, more molecules have a kinetic energy greater than the activation energy. Therefore, the reaction should proceed at a faster rate. We have also looked at how catalysts affect reactions. What a catalyst does, remember, is it's going to lower the activation energy, which means my required threshold speed moves from here down to some slower velocity, perhaps here. And if this becomes my threshold velocity, and molecules moving faster than it are capable of reacting, then for every curve, more molecules have sufficient kinetic energy. So both increasing the temperature and adding a catalyst have the same effect, but for different reasons. For increasing temperature, it's going to increase kinetic energy. For adding a catalyst, it's going to lower the activation energy.